pipes. We found some pipes that were still there, actually, which hadn't been taken by previous archaeologists. So we need to study the hydraulics of the drainage systems. Thank you.
Excellent. Okay. Let's thank you again. So we move forward, and our next speaker is Flavia Tauro, and the topic is very, very different. So we go from archaeology, we go to engineering, and Flavia has been involved with H2CU in 2 programs. She has earned her master degree in MIT in environmental engineering, and now she's pursuing her doctoral degree in collaboration between University of Rome La Sapienza in hydraulics and in mechanical engineering at NYU Poly. So,
okay, thank you, Professor, and good afternoon, everyone. So my talk is going to be on novel observations in hydrology. So, thank you. First of all, let's take a look at what the major challenges in hydrology currently are. So hydrologists are focusing on environmental changes, and specifically what the water cycle changing dynamics are in connection with changing human systems. And this would mean observing and understanding such processes through novel measurement techniques. And this leads us to our next slide, where an interesting class of measurement techniques are presented. And these are tracers. So what are tracers? Tracers can be either artificial or natural compounds or elements such as isotopes or chemicals or dyes that can be either naturally present in the environment or can be artificially deployed. So an instance would be, as you can see in the top right figure, trying to shout.
So can you hear in the back? Not really. Good.
Yeah, you have to talk close to the mic, very close.
You can also stand and hold it.
Okay. Can you hear me now?
Yes.
We're good?
Okay, so how are tracers typically used? For instance, as you can see in the top right figure, an application of using a tracer would be deploying it at a certain spot in a river and then going downstream and taking samples. And then taking, for instance, the concentration of salts or chemicals and from the comparison of the concentration, trying to infer important parameters such as flow velocity or travel time or other parameters. So what are their major drawbacks? So the major drawback is that they require sampling, so the physical presence of a human being going on site and taking samples of water and then going to the lab to analyze it. Another alternative is that instead of taking samples of water, we can deploy probes or equipment in the river. But can we take measurements with probes when there is a flash flood or when there is heavy precipitation? This is not ideal. Another drawback is that they tend to disperse, either for dilution in a river, for instance, or for adsorption to natural sediments. And another important thing is that they only provide localized measurements. Most of them only provide localized measurements, so at a certain point in space. So this leads us to the main focus of my doctoral thesis. That is the development of a novel tracing methodology. As you can see in this cartoon, what we have tried to work on is the development of a new tracer that is versatile, so that can be used on overland flow or stream flow, and is non-invasive. So it doesn't require the presence of operators or invasive probes. And is hopefully suitable for continuous, fully automated, and also available at larger scale measurements. Larger scales that are typical of hydrological systems. Okay, so more specifically, this is what the tracer is based on. So as you can see, these are pictures of particles. So the tracer is a particle tracer. The particles are fluorescent, and their main advantages are the fact that they are highly visible, and this means that we can detect them through the use of digital cameras, for instance, and that they are insoluble, so they do not disperse or adsorb to sediments. So on the top figures, you can see off-the-shelf particles we bought, and in the bottom figures, you can see particles we have in-house fabricated in our lab, and that are completely eco-friendly and biodegradable, and are made of beeswax. Okay. So what's the next step? The next step has been how do we detect and track the motion of the particles? So we have developed a simple set of tools based on image analysis, such as the ones you are currently looking at. So this is a global index that gives the brighter pixels in an image. And these pixels are highly probable to pertain to the presence of the particle. So this works as a particle detection instrument. In this slide, instead, you can see a schematic of the tracking procedure we have developed at during my doctoral program. So this tracking procedure is based on the assumption that we already know the shape the particle is going to have in the video we acquire in the environment. Then we perform a correlation search inside the image, and the pixels where the higher correlation coefficient is retained are more likely to pertain to the actual position of the particle in the image. Okay. What we've done is trying to assess the feasibility of using such tracers in a real context. So the first questions have been, can we see the particles if we use it as a stream flow tracer? So this means in the presence of high flow regimes and in the presence of light reflections, foam, and bubbles. So as you can see, the first proof of concept experiment has been conducted in this small watershed in the Italian Alps. And I'm going to show you a video of the actual experimental campaign featuring Professor Grimaldi.
Start.
Oh, wow. We have some music as well. So this is the record done at the...
We always put
In a deep and dark December.
This is the record done at the measurement station, and this is how the particles look like when they pass underneath the sensing station. This is Professor Grimaldi performing an experiment with a dye. So what we did is comparing our measurements or our findings by using the particles with some more established tracing methodologies such as dyes. Okay, so going back to our presentation. Okay, so this is the sensing station we have developed that integrates an array of UV lights and a camera for the acquisition of the particle transit. The next question we are trying to answer through experimental campaigns is, can we see the particles in the presence of turbidity and under the effect of rain? And to answer these questions, we have performed another experimental campaign on a small-scale hill slope in Viterbo, where rain was simulated through this rainfall simulator you can see in the bottom picture. So we had the particles deployed at a section on top of the hill, and then our sensing station on the downstream section of the hill. So as you can see here in these figures, this is how the particles look like when they transit underneath the sensing station. And on the bottom left figure, you can see the time series of the index for particle detection I've showed you before, where the peak corresponds to the actual transit of the particles. And this is a kind of an outlook on the future research we're going to work on. So the first step would be the fabrication of more biodegradable particles and edible so that everyone can eat them. And then the integration of the sensing system you've seen before, for instance, in the Rio Cordon watershed experiments, in an unmanned aerial vehicle as the hexacopter and quadcopter you can see in the top figures. And the top right figure you can see is depicting a quadcopter we're currently developing at the DSL, the Dynamical Systems Lab at NYU Poly. The other step I'm currently working on is the application of machine learning algorithms for flow identification. And this is snapshots of von Karman vortex street past a circular cylinder, some experiments I was working before coming here, actually. And thank you for listening.
Okay, so any questions for Flavia? Some questions are good. Professor Natale, again, you can ask.
Questa volta devo dire in italiano.
Prova a dire in italiano, poi per Salvatore traduce.
No, perché diciamo l'uso dei traccianti.
The use of tracers.
Tutto quello, l'uso dei traccianti è molto più, come dire, importante, perché è un problemino risolto, non c'è stato di farlo, almeno che sappia la Segretaria. Nel caso di flussi granulari, e allora all'interno del flusso granulare non si può vedere in nessun modo, tranne che con delle tecniche innovative. Quindi suggerirei di sviluppare questa idea che in maniera, come dire, assolutamente innovativa e che richiede un'applicazione molto ingegnosa, che però penso che siate capaci di fare.
Puoi tradurre anche domanda? Una risposta, no?
Okay, it's a very interesting comment, actually. So it's the like proposing the. I hope so. I'm trying. It's the application of tracing systems to granular flows, since no other measurement systems can be applied in such flows. So we'll definitely consider that. Thank you for suggesting.
Okay. Thank you. Okay, and our next speaker is Anna Laura, I think, right? Yes. Aspetta. Come sono parato? Okay. So, our next speaker is also an engineer, and she's a postdoc currently at the University of Perugia, and she has been involved in an ample spectrum of activity within the H2CU that allowed her to develop strong collaboration between the US and Italy. So she has collaborated with City College in New York, she has worked with Columbia, and now with Virginia Tech. Her work is focused on building energy efficiency, dynamic simulation of thermal energy behavior of buildings, cool roof technology and innovative materials for optimizing building envelope properties through continuous monitoring and life cycle assessment. And she's also the founding member of the International Building Performance Simulation Association in Italy. So let's welcome Anna Laura, and thank you.
Thank you very much for the introduction. Given the huge amount of energy consumption imputable to the building sector, and also the important shift of the population from the rural areas to the urban areas, the research issue around the investigation about the energy efficiency of buildings and about the formulation of some models in order to predict the thermal energy performance of buildings, especially when they are located in urban areas, has become very important. To this purpose, actually, we elaborated a sort of reliable methodology that we named interbuilding effect, which purpose is to predict and to evaluate the thermal energy behavior of buildings, especially when they are located in very dense urban area. Thus, the research questions we addressed through our multiple studies we carried out here in the US and in Italy was basically concerning does this kind of interbuilding effect exist, and also which is the impact of this kind of interbuilding interaction in terms of indoor operative temperature and energy consumption. And we also analyzed which is the impact of this on effect with respect to different climate conditions, local and global climate conditions, and also with respect to different urban morphologies. We also included in our assessment also some assessment concerning the inter-occupant relationships. Thus, the methodology basically concerns a first preliminary urban assessment, then it concerns a deep analysis of the architecture, of the technical and the physical properties of the buildings in order to elaborate dynamic modeling and actually dynamic simulation of the building we investigated, and finally to provide a deep analysis of this kind of effects. The first case study we actually analyzed consists of 20 single-family residential buildings. They are real actually, and they are located in Albany, New York. Thus, on the right side of the slide, we can see the first results, and so the gray lines concern the thermal energy analysis of the single building that we consider as the control building, and the black lines represent actually the thermal energy behavior of the same building when it's considered within its real urban context. And thus we can see a very huge amount of indoor operative temperature difference, especially during the afternoon, because it's reached something like 8 Celsius degrees, while the most important interbuilding effect is represented by the difference of the solar radiation entering through the windows, while there is also a not negligible effect in terms of the dynamics of the opaque wall of the building. Here we can see the analysis of the interbuilding effect with respect to different climate conditions, and so we took into account the hottest climate condition in Miami, Florida, and the coldest climate condition in the US, and so Minneapolis, Minnesota. Here we can see that the interbuilding effect in Miami corresponds to a sort of discrepancy between the primary energy requirement for cooling of the building considered as a standalone entity with respect to the same building when it's simulated, modeled and simulated within its real network, and so with the building surrounding the control building. And so also in Minneapolis the interbuilding effect is actually absolutely not negligible, and both for the estimation of the primary energy requirement for heating and cooling, and the difference reaches about 22% during the heating season. The second case study actually concerns the same physical environment and so the same residential block located in Albany, where we also added a sort of affiliation network theory model. And so we were able to answer the fourth research question, and so how the inter-occupant relationships can impact building energy consumption, especially to guide for further energy conservation. And so we elaborated a sort of model, also experimentally validated through an experiment we carried out at Columbia 2 years ago, where we defined the interpersonal closeness index. Thus, in the yellow rectangles, we can see our results concerning the further energy saving produced by the closeness of the occupants of the building's network. The third case study concerns the One Worldwide Plaza here in New York City, and so it consists of a residential building that is the shortest one of the lower graph and lower picture, and the office building that is the tallest one. The complex is located in Hell's Kitchen here in New York City, and we were able to perform a sort of interbuilding effect analysis taking into account different urban locations, and so modeling these two buildings in the urban context of Soho, the actual context of Hell's Kitchen, and also in the very dense urban areas such as the Tier 3 district. And we were also able to actually analyze which is the impact of the local climate condition with respect to the weather characterization of the city. Here there are the results concerning the primary energy requirement for cooling and heating of the office building, where we can see that the difference produced by the interbuilding effect is more or less 25% during the cooling season, while it reaches about 12% during the heating season. And here we can also see the growing trend of the interbuilding effect with respect to the growing urban density we took into account. While together with the analysis of the urban morphology and its impact, we also carried out a sort of local climate analysis in order to elaborate realistic weather boundary conditions for our dynamic simulation models. And so we actually took into account both the experimental data that are currently measured in several weather stations located around the city, and also we actually validated this kind of experimental data through the theoretical method elaborated by the Earth Institute at Columbia University, in order to determine which is the error that is usually carried out when you perform a sort of thermal energy dynamic simulation without taking into account specific urban climate context, such as the urban Italian phenomenon that characterize so much the New York City weather conditions that are very much warmer with respect to the surrounding rural area. And thus we were able to estimate here in the graph is reported the cumulative error that is usually carried out if you are not taking into account both the real urban morphology surrounding your building and also the real urban climate characterization. The first case study concerned the application of our model to an Italian case study, and so we choose three multi-family residential buildings in Italy, especially in particular in Perugia, which is a middle-sized typical Italian historical city with a middle-age period of construction of the historical center we see in this picture. And we, through actually thermal energy dynamic analysis, we were able to estimate which is the thermal impact of this kind of interbuilding effect. And here we can see that it reaches 4 Celsius degrees in summer in the very dense urban area. And this kind of effect is actually very much higher during the summer because the main effect is produced by the mutual shading between phasing building especially, but also between among all the buildings that are located in close proximity with respect to the control building. But there is also an important result concerning the medium density area, and while in analyzing the non-dense area, actually the interbuilding effect could be considered as something like almost negligible. The fifth case study concerns an ongoing research we are carried on with Columbia University and Virginia Tech, and we are trying to organize all these kind of results concerning the interbuilding effect extent in order to elaborate a sort of GIS mapping around the city of, actually around the first neighborhood of Manhattan. And so we are elaborating this kind of layer in order to perform a sort of useful tool that could be used by designers, policy makers, or energy planners or urban planners, for example, in order to estimate which is the energy consumption of the building and also which is the energy consumption, the variation of the energy consumption and the energy performance related to the interbuilding effect in the different areas of the city. Thus, starting from the consciousness about the building huge energy consumption with respect to the total global energy consumption and to the progressive shifts of the population to the urban areas, we proposed a sort of methodology in order to take into account which is the impact of surrounding building with respect to the thermal energy performance of the building we are studying. And so we are trying to develop a sort of a simple and useful tool in order to actually to promote this kind of analysis and to actually make the researchers and designers aware about this kind of phenomena, because it has the same grade of magnitude of the common retrofit interventions. And so thank you very much for actually making this kind of research possible, and the cooperation already alive, and thank you for your attention.
So any questions for Anna Laura? Yes, very good.
Yeah, I have some questions about, I mean, I know you're early on in your research, but have you actually seen effects of these LEED buildings, like within the architecture world, or these green roofs, or vertical gardening? Like, is that starting to actually impact the heat within the urban environment?
Yeah, we here I just reported some results about that, but given that we actually found out so important difference between the thermal energy model of just a standalone building with respect to its context, we are deepening, especially your actually analysis about the green facade, green roof, and we are also taking into account different kind of wind motion and wind velocity, specific local phenomena. Yeah. And also actually the mutual reflection between phasing facades, and especially because high reflective facade and also absorbing or several kind of reflections produced by facades materials such as grass for building facade, green facades.
Kurt?
On this inter-building effect, is there any seasonal change between summertime and wintertime? Summer when you have air conditioning blowing, and in the winter when you have these very inefficient buildings that are heated with old steam systems?
Yeah, there is an important difference between the summer and the winter condition. In fact, actually, in summer we find out a sort of benefit produced by the mutual shading of the closed building, and so it's able to reduce the energy requirement for cooling, but it's also able to make the energy plants performing in a very low efficient way, because they are designed for covering a sort of huge amount of energy requirement for cooling. But the actual operations are very much different for this kind of interbuilding effect. While during winter, in no sunny condition, actually the interbuilding effect has a lower impact in terms of mutual shading, but there is also a huge impact in terms of modification of the natural flow of the air produced by urban canyon or something like that. And so it could be, there are different phenomena.
Very good. Okay, let's thank Anna Laura again. Thank you. Grazie. So when we move to our fourth speaker, who is Benedetto Argento. So, open there. So Benedetto is a master student in Columbia University. He's participating in a dual degree with the University of Bologna in civil engineering, and he'll tell us a little bit more about his research under the supervision of Professor Raimondo Betti at Columbia University and Professor Francesco Bertini from University of Bologna. And this I cannot say, it's very difficult, but from Mukhopadhyay, you say better, from Columbia University. Okay, so thank you.
I even don't know his name. So. Good evening, everybody. My name is Benedetto Argento. Today I am going to annoy you about some stuff related to structural identification and some of the outcomes of my research on this field. The starborn complexity of the design reached today by the civil engineering keeps increasing the need of high-quality structural behavior provision that needs to be satisfied, and this parameter is strictly related to the importance of a model. Models that, as you may know, it's really related to assumption on mass, stiffness, materials properties and constraints. And each of these assumptions is related to uncertainty. And the awareness of this kind of situation has led in these last 10 years, joined with the need of monitoring of constructed system, to give more and more importance to observation and use of experimental response data. Actually, structural identification is just an iterative procedure that consists in a development of a model that is depending on some finite number of parameters. These parameters are defined and updated. Actually, the updating is done by some dynamical or static tests, testing that are usually expensive, and from which the eigendata of our building or our structure, let's say the main information related to the system, are updated and used to validate the model. One of the most common validation technique is the minimal realization, that today for us it will be just a model capable of taking the input and the output of a system and find the relation between these two items. Actually, is just to understand what is it. It is going to give us the mass, the damping, and the stiffness of the system. Another way to look at the structural identification, in my view, maybe the most interesting, is the damage identification. The damage identification, in order to get the point, we can talk about an example. Let's say to have monitored a structure and to know all the model parameters of this system. If we assume that an event is going to affect our structure, and we reperform the structural identification after that event, hopefully the mass will be the same if no local collapses are going to happen. Slightly, maybe the same damping, maybe is going to increase due to some plasticity in steel and in cracks in concrete. But anyway, the major changes are going to be in the stiffness matrix. And we can be able to compare the new stiffness matrix and the old one, and thanks to the topology that should be known, we can even identify local damages that are not visible in reality. As you may know, reality is always a lot more expensive and more complex. So usually it's not affordable to put a couple of sensor actuator at each DOF of our DOF or our system, and so usually we should choose a strategic location of this couple of actuator sensor. An actuator is a device that is able to excite the system, and a sensor is a device that is able to record the time variation response of the system itself. Since we have to make these choices, we developed with Professor Betti a theory based on the error generated by missing modes. We develop a theory that ends up with a sort of sensibility parameters. Now, just forget about the mathematical expression. Let's focus on the physical medium. We have two kinds of parameters, the alpha ik and beta I. The first one, it indicates it's an index proportional in its value to the influence of the mode shape k to the degrees of freedom I. So the higher is its value, the higher is the influence of the mode shape k at this DOF. So if I want to catch the mode shape k, I should locate the sensor and the actuator at the DOF that has the greatest value of the alpha parameters. As far as the beta one is a more general concept, but is basically the same. It's just related to catching the overall behavior of the system. Just to let you know how it works, we have performed a Monte Carlo simulation on a 10,000 sample system, taking into account a 7 DOFs system. The theory is applicable to any number of degrees of freedom. We enforced parameter distribution to give some standard deviation, and these are mainly the results. If we want to catch the overall behavior of the system, so to note all the mode shapes of the system, as you can see in the left side distribution, we should put the actuator sensor location at the first DOF, that is reasonable, I mean. You can notice the difference in the ranges value between the other beta i's. As far as the other outcomes are related to the catching of mode shape number 1, that usually is the most important in a system or in a building, in a bridge. If we want to catch the first mode shape of the system, we should put the couple of actuator sensors at the top floor of our building. This analysis has been performed for each DOF and for each mode shapes, and the idea in reality is that you can pick your eigendata directly from your finite element model, and then you can perform this theory, this analysis, this sensibility analysis, and it is going to tell us where you should put your couple of actuator and sensors. To conclude, I would like just to mention a discovery that we have made with Professor Bertini, Professor Betti, and the other guy from Columbia. We discovered a new relation that allows us to to pass directly from the complex mode shape that are given throughout ERA OKAD based approach that is like a structural identification approach. And we can, by means of this relation, get directly the real mode shapes of a system. I'm not going inside the math of this stuff, but if you are interested, you can contact me after this presentation. We found this relation. We tested it for a lot of number of systems with positive results. So it works. Thank you for your attention.
Any comments or questions for Benedetto? Okay, so I can ask them.
Can I just ask
Sure.
a question? So you made an experiment on the structure, or is it just?
Actually not. They are just simulation based on the MATLAB environment. The theory is totally analytical, so it works analytically. The testing stuff, that I mentioned, is related to the MATLAB environment, but is related to
the signal, a randomic signal.
Yes, a forward problem, and we compare the results between our relation and the actual one that came from an eigenvalue problem. I mean.
And then you pass it from the frequency domain.
Yeah,
to the
If
domain of displacement.
Yes.
Okay.
Model coordinates.
So, what is, in order to measure something which is above the uncertainty of the instrument, how severe needs the damage to be?
Actually, I'm not so deep inside to answer your questions. But when a damage occurs that is not more than 10%, it is usually identifiable. If it is more than 10%, you should replace something, so it is going to be visible. To be detected by this procedure, I think around 1–2%.
Okay.
Thank you.
Let's thank Benedetto again. And last but not least, our last speaker is Giancarlo Gramazio, who is a master student in a dual degree program between Polytechnic of Bari and mechanical engineering at NYU Poly. He's conducting research in the mechatronics lab, and he'll tell us a little bit more about his work. Spegni qua.
So, good evening.
Parla vicino.
Good evening, I'm Giancarlo Gramazio, and I'm going to discuss my master project, Control of a Robot Arm using a sensor sleeve, in the mechatronics lab with the professor Vikram Kapila. So, there are two important topics in my master project, which are the mechatronics and the control of the robot arm. As far as mechatronics is concerned, I'm designing the sleeve of to make the robot move, and on this sleeve there are some embedded sensors that can measure the position in time of the human arm, so that the robot can move exactly like the human arm. There are two microcontrollers which are communicating with the Wi-Fi. I'm especially caring about the control of the robot arm, in particular applying a kinematic model, especially caring about inverse kinematics. And I also develop a Simulink model so that the robot can move exactly like the human arm. Then the components which are required to move the robot are 4-5 degrees of freedom robot, which has to simulate exactly the movement of the human arm. The human arm, we know, has 7 degrees of freedom, 3 in the shoulder, 1 in the elbow, and 3 in the wrist. So our robot has like 2 or 3 degrees of freedom less than the human arm. Then required also 2 Arduino microcontrollers, which are able to make the sensor work on the sleeve and to measure the position of the arm. These Arduino microcontrollers can communicate using a Wi-Fi shield. So making a Wi-Fi code, it's possible to make them communicate. Then are also some sensors, gyroscopes and accelerometers, which can measure the angles between all the links in the human arm. Then there is a servo controller which can make the robot to move really smooth and close to the movement of the human arm. And of course, it's required a skin-tight sleeve so that the measurements made on the arm are good enough. So to make the robot move are required 5 steps. The first step is the data acquisition. So again, we can measure in time the angles between the links in the human arm, and we are able to compute the position of the wrist just applying the forward kinematics. Then this data are transmitted from the Arduino on the sleeve to the Arduino connected to the robotic arm. Then there is a code on Simulink that I developed that applying the position of the wrist is able to compute all the angles between the links of the robotic arm, so that it's able to get that position. And then this data are transmitted from Simulink to Arduino of the robot. These are 2 examples of robot that I'm going to control. The first one is a Lynx robot which has 4 degrees of freedom, and I'm controlling it just because it's small and it's easy to work on it. As we can see, it has 4 degrees of freedom, 1 in the base, 1 is this one, which is in this joint, which can simulate the movement of the shoulder. Then there is the servo motor, which can simulate the movement of the elbow, and the last one is the wrist. At the end of my study, I'm going to control the CRS robot, which has 1 degree of freedom more, which is a rotation in the wrist. So one of the most important part of my work, as I said before, is the development of the kinematic model. I applied a Denavier-Hartenberg representation so that each frame, so that I applied some rules to get some frames in each joint of the robotic arm. Then I computed all the transformation matrices to relate the position of the wrist of the robot arm with respect to the base frame in the shoulder. Then I found these relations, and considering the position of the wrist to be known, I was able to get the relation between a clean expression between the angles between the links of the robot to the position of the wrist. These equations have been solved analytically so that the time required for Simulink to solve it is really small, so the computational time is low. The final goals of my studies are, of course, plane operations like writing, so the robot will be able to move, to write exactly like a human arm, and of course 3D operations like pick and place. So the robot will be able to pick up an item and replace it in another position. The possible applications for these kinds of robots are several. In particular, it's important for the assistance for people with disabilities, because nowadays we know that these robots can give benefits to people that are unlucky and they have disabilities. Another important application can be in for operations in harmful environments, like places where the temperature is too high or where there are gases which can be dangerous or poisonous for people to work. Before ending, I just want to show a video which is a comparison between a simulation in Simulink and the real movement of the robot. The movement is clear, is linear along one direction, and as we can see, the movement of the robot is not as smooth as the one of the simulation in Simulink. This is due to the fact I'm not using the servo controller yet. Okay. 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 So, thank you. Any questions?
Very good. Okay. Any questions for Giancarlo? Yes.
How much time is it going to take to complete all the project?
To compute what?
To complete the project, how much time do you think it will take?
I think 6 months, so it will be for the end of August. I think so.
Yes, Paolo.
I would like to know the manual to control the zero shift.
The zero shift.
About the accelerometer and the gyroscope. Otherwise, all the measurements are just garbage. Zero shift means that the accelerometer, when you continue to integrate,
yeah,
there is an additive effect of the error, and so you cannot control properly the position of each arm. So the problem of compensation of the effect of the error. You adopt.
Yeah, I'm using Simulink, so no, just using some transfer functions to replace the noise and every problem in the measurements.
Any other comments? Yes, please.
What is the difference between the movement of your arm and the robot arm?
Actually, now is high, but I need to improve some the movement using the servo controller so that and also I have to minimize the time in the acquisition of the data so that the movement will be close enough to that one of the human hair. Okay.
Very good. So let's thank Giancarlo again. Okay. So before we wrap up, I think we want to thank again these 5 excellent students. And